Welcome to our guide on multivariate Garch modeling in Stata. Today, we will explore the theory, practice, and forecasting applications of these powerful models. Our focus will be on understanding how to model the co-movements of volatility and the dynamic correlations between multiple time series, a crucial task in modern finance and econometrics. In financial markets, assets rarely move in isolation. A shock to one company or sector, like a supply chain crisis affecting Toyota, will inevitably spill over to its competitors like Nissan and Honda. This is the principle of interdependence. Standard univariate Garch, generalized autoregressive conditional heteroscedasticity, models are limited because they analyze each time series in isolation. This approach completely misses crucial dynamics like portfolio risk and financial contagion. The solution is the Multivariate Garch, or MGARCH model. These models directly estimate the entire conditional covariance matrix, which we denote as HT. This matrix captures the evolving volatilities and correlations between all assets in the system simultaneously. During the 2008 financial crisis, the correlations between almost all stocks, regardless of sector, spiked dramatically. A univariate Garch model for a single bank stock would have captured its increased volatility, but missed the systemic risk shown by the rising correlations across the entire market. However, modeling the entire covariance matrix is complex. There isn't just one MGARCH model, but a whole spectrum of them, each with a different trade-off. Let's look at this spectrum next. This slide illustrates the spectrum of MGARC models, ranging from the most parsimonious to the most flexible, and highlights the fundamental trade-off we face. On the far left, we have the CCC, or Constant Conditional Correlation, model. This is the most rigid and parsimonious, meaning it requires the fewest parameters. It assumes that while individual asset volatilities can change, the correlation between assets remains constant over time. It's simple, but often restrictive. Moving to the middle, we find the DCC and VCC, or Dynamic and Varying Conditional Correlation, models. These are often considered the sweet spot because they allow correlations to evolve over time, offering a more realistic representation of financial markets. They strike a good balance between realism and estimability. On the far right is the diagonal vech model. This is the most flexible and parameter-heavy, as it attempts to model every single covariance directly. While this offers maximum flexibility, the number of parameters explodes quickly with the number of assets, making it very hard to converge for systems with more than 3 assets. This brings us to the crucial trade-off section. The general MGARC model is incredibly flexible in theory, but this flexibility comes at a cost. Not all parameters can be reliably estimated in practice. Therefore, we must choose a parameterization that carefully balances the desire for realism with the practicalities of computational feasibility. Given these choices, how do we select the most appropriate model for our specific research question and dataset? Let's look at a decision flowchart next. The first and most critical question is, do you believe the correlations change over time? If the answer is no, the CCC model is your starting point. If you expect correlations to be dynamic, the next question is about the size of your system, which we call N. For small systems, say 3 or fewer assets, the highly flexible DVECH model might be feasible. For larger systems, which are common in finance, you'll typically choose between the DCC and VCC models. These models are more parsimonious and have a better chance of converging. A good rule of thumb is to start with the DCC model. It's more realistic than CCC and more parsimonious than vech. After estimation, you can use information criteria like AIC or BIC with the StatIC command in Stata to formally compare the fit of different models. The core of conditional correlation models is this decomposition equation. HT equals dt to the power of 1/2 times RT times dt to the power of 1/2. HT represents the conditional covariance matrix, which is what we want to estimate. dt is a diagonal matrix of variances, where each element on its diagonal, sigma squared IT, follows a univariate Garch process. RT is the conditional correlation matrix. In constant conditional correlation, or CCC, models, RT is a constant. In dynamic conditional correlation, or DCC models, RT evolves dynamically based on standardized residuals. The intuition behind this formula is to separate the volatility of individual assets, represented by DT, from the dependent structure, or correlations between them, represented by RT. This two-step estimation process is crucial as it makes the model stable and estimable, even for large datasets. The first core assumption is stationarity. Like most time series models, MGARCH requires the input series to be stationary. This is why we almost always model asset returns, which are typically stationary, rather than asset prices, which are non-stationary. You can check for this using tests like the Dickey-Fuller test, or D-Fuller in Stata. The second assumption is positive definiteness. The estimated covariance matrix, HT, must be positive definite at every point in time. This is a mathematical requirement to ensure that the implied variances are always positive and correlations are between -1 and 1, which is necessary for valid probability calculations. When specifying the model, you must choose an error distribution. The default is the multivariate normal distribution. It's efficient if your data truly is normal, but financial returns are famous for having fat tails, meaning extreme events happen more often than a normal distribution would predict. For this reason, the multivariate student's t-distribution is often a better choice for financial data. It has fatter tails and can better account for extreme market movements. If in doubt, especially with financial returns, it's generally safer and more robust to use the student's t-distribution. The alpha coefficient, from the ARCH term, represents the reaction to news or shocks. It measures how much a shock or large residual from today affects tomorrow's volatility. A large alpha indicates that volatility is spiky and reacts strongly to market events. The beta coefficient, from the GARCH term, represents the memory or persistence of volatility. It shows how long the effects of a shock linger. A high beta, typically above 0.9, means that shocks die out very slowly and volatility is highly persistent. In dynamic correlation models like DCC, you will also see lambda coefficients. These govern the adjustment of the correlation matrix over time. If these parameters are statistically significant, it's strong evidence against the constant correlation assumption. For the model to be stable, the sum of the lambda parameters must be less than 1. It is crucial to remember that MGARCH models describe comovements, not causality. A significant positive conditional correlation simply means the two assets tend to move together. It does not mean one causes the other to move. This means a positive conditional correlation indicates that returns on these stocks rise or fall together, as stated on the slide, but this doesn't imply a causal link. For example, if you find a beta of 0.98 for the volatility of the stock market, it means that if there's a high volatility day today, perhaps due to an unexpected political event, the volatility is expected to remain high for a long time afterward. The market doesn't just calm down overnight. We've mentioned the DVECH model as the most flexible. Let's now take a closer look at its main challenge and how we can manage it. The main challenge with diagonal vech models is that they directly model every covariance. This leads to a rapid increase in the number of parameters to estimate, growing at a rate of n squared, where n is the number of assets. This parameter proliferation makes DVECH models computationally intensive and often impractical for systems with more than a few assets, as they struggle to converge. The solution to this complexity is to employ linear constraints. Constraints allow us to impose specific restrictions on the model's parameters. This can be done to test economic theories, such as whether two assets have the same volatility dynamics, or simply to reduce the overall number of parameters, which significantly aids in model convergence. For instance, you could test if two assets, say Y1 and Y2, share identical volatility dynamics by imposing a constraint that their arc parameters are equal, as shown in the Stata example. Constraint 1, lil arch 1, 1 equals lil arch 2, 2. Then you run the DVECH model with this constraint using MGARCH DVECH Y1, Y2, constraints 1. This approach helps manage the complexity of DVECH models, making them more feasible for analysis and hypothesis testing. The basic command in Stata is MGARCH. You first specify the model type, such as DCC for Dynamic Conditional Correlation, CCC for Constant Conditional Correlation, DVECH for Diagonal Vech, or VCC for Varying Conditional Correlation. Then, you list your dependent variables, optionally followed by independent variables for the mean equation. The arch-lags and GARCH-lags options are used to specify the order of the variance equation, just like in univariate Garch. Arch1 and Garch1 is the most common specification. There are several key options. Distribution T is crucial for switching from the default normal distribution to the student's T distribution, which is recommended for financial data. The DVECH option allows you to include variables that affect the variance directly, which is known as multiplicative heteroscedasticity. A useful syntax tip is that you can specify different mean equations for each dependent variable, as shown in the example, which adds a lot of flexibility. For example, y1 equals x1, y2 equals x2 allows for different regressors in the mean equation for each asset. Our scenario involves modeling the daily returns of 3 Japanese car manufacturers, Toyota, Nissan, and Honda. We'll start by loading the dataset from the Stata Press website using the use command. Before any modeling, we must run through a critical checklist. First, ensure the data is numeric and there are no gaps in the time series. Gaps can cause major issues for time series models. Second, and this is absolutely crucial, you must declare your data as a time series using the tssetDate command. MGARCH commands will not run without this step. Finally, as we discussed, verify that your variables are stationary. We are using returns, which typically are, but it's always good practice to visually inspect the series, which we can do using the line command to plot Toyota and Nissan returns, and run formal tests if needed. Here, we move to the second step of our process, estimation, specifically focusing on the Dynamic Conditional Correlation, or DCC, model. We fit a DCC model with AR1 mean terms for each return series and GARCH11 variance specifications. The Stata command for this is shown, MGARCH DCC, followed by our variables, Toyota, Nissan, Honda, and their first legs for the mean equation, then Arch1, Garch1 for the variance equation, and no log to keep the output clean. The DCC model follows a two-step process. First, it estimates univariate GARCH models for each series, then uses the standardized residuals to estimate the dynamic correlations. A common issue you might encounter is a not concave message, which indicates the optimizer is struggling to converge. If this happens, try simplifying the model, checking your starting values, or, a robust solution, switching to the student's T distribution using the distribution T option, which is often more suitable for financial data. After estimation, we focus on the adjustment parameters, lambda 1 and lambda 2. The key is to look at their p-values, shown in the p greater than z column. In this output, both lambda 1 and lambda 2 have p-values of 0.000, which are highly statistically significant. This provides strong evidence that the correlations are not constant over time. Therefore, our choice of a dynamic model like DCC over a simple CCC model was correct. We can also look at the sum of the lambda coefficients. Here, the sum is approximately 0.024 plus 0.954, which equals 0.978. This value is very close to 1, indicating that the dynamic correlation process is highly persistent. Shocks to the correlation structure will take a long time to die out. The takeaway here is clear. The data tells us that the financial relationship between Toyota, Nissan, and Honda is not static. The degree to which their stock returns move together changes significantly over time, invalidating the simpler CCC model. Interpreting coefficients is insightful, but the real power of these models comes from their ability to forecast. Let's see how to do that and visualize the results. After fitting the model, we can perform dynamic forecasting. First, we use TS-append to add future time periods to our dataset for the forecast horizon. Here, we add 50 periods.
The predict command is then used to generate the forecasts. We can forecast the conditional variance using the variance option and, most importantly, the conditional correlation using the correlation option. The dynamic option tells Stata to start the forecast from a specific date. Visualizing these forecasts is incredibly powerful. Plotting the predicted conditional correlation over time often reveals patterns that are invisible in raw data. For instance, we can clearly see how correlations between assets spike during periods of market stress or crashes. This is a critical insight for risk managers. Simpler models that assume constant correlation would completely miss these dynamics, leading to a severe underestimation of portfolio risk during crises when diversification benefits tend to disappear. A common issue in econometrics is model misspecification. In our case, what if the true error distribution is not perfectly normal and not even perfectly student's t? If the distribution is misspecified, our standard errors could be wrong, leading to incorrect statistical inference. The solution in Stata is simple yet powerful. Add the VCE robust option to the estimation command. This option calculates robust standard errors. Using VCE robust effectively turns the estimator into a quasi-maximum likelihood, or QML, estimator. The remarkable property of a QML estimator is that it provides consistent parameter estimates and reliable standard errors, even if the normality assumption is violated, as long as the mean and variance equations are correctly specified. Comparing the standard output A with the robust output B, you can see that the coefficient estimates for lambda are identical, but the standard errors have changed slightly. This can affect the Z statistics and our conclusions about significance, making robust errors a safer choice. First, always begin with proper data preparation. This means ensuring your data is t-set and, most importantly, stationary. Next, select the appropriate model. Use the flowchart we discussed to decide between models like DCC and DVECH based on your research question and the size of your system. Then, refine your model. Consider using the student's t-distribution for financial data, and always use robust standard errors with VCE robust to protect against misspecification. Finally, don't just look at coefficients. Visualize your results by plotting dynamic forecasts of correlations to gain deeper insight.